Gadget UK here again, back for part 4 of the Marine, which is an Amber recreation for the Amiga 3000 and the GBA1000. It'll go in the 3000T as well, and there was a card that Commodore created that used one. And there was at least one third-party scan doubler that I think used one or more Ambers. You could put 2 of them on there, I think, to get AGA. Just picking up here, showing you a clip that I forgot to include in the previous part. So when I first built the prototype and I got the code base set up, you know, and compiling, the very first thing I did was output a fixed colour to the screen in order to display something. And yeah, that's what this first section of the video is here. Right, this is a bit of a mess. I've got it set up on my PC here, switch it on, and I'm doing the Xilinx programming that way. I've just forced it to just try and display a white screen, which was working a minute ago. Now it's not. It's like it's intermittent in terms of how it syncs onto the signal. You can see right now though we're just getting nothing. Yeah, the output to the DAC, I've kind of forced it. Oh, there you go. To do a white screen. That is actually working. We're getting white pixels on the output. But it's not right in relation to the sync, I think. I'm just touching the top of that chip. Yeah, anyway, I can prove that further now by, and look, every now and again it goes nuts because it's not synced right. But white is the thing there. I'm now going to change that to red because I've never seen red, so let's just give that a go. And this probably isn't the right place to do this. It's in, you know, in the signal process bit for one of the clock signals. But anyway, I'm doing that every single time, every single loop or whatever there. It's not really a loop. It's just, it should just set them to red. Should set those red output bits to high and the green and blue to low. And using impact here, it takes an absolutely ridiculous amount of time to program up this way. It's quicker to copy the files to the PC, you know, Win 10, and do it from there. Right, exciting moment again, although it's going to be glitchy if it works. Let's see if we get red now. I'm not sure if it needs a power cycle. Let's try power cycle. We've got green. But we've seen green before, it's red I'm looking for. Look, it's just the monitor. Because I'm using a scan doubler on the monitor to increase the, you know, to handle the resolution basically. It's like we had white, why can we not get red? We've got blue, look. So the GBA1000 is proving to be a wee bit flaky when it warms up. Now I did kind of experience this when testing, but I thought I'd resolved it with a 50MHz crystal. Seemingly not, so I'm just going to quickly take the board out and I'm going to attempt to remove the resistor on DTAC, because you know what, that went on very early on and I suspect that might be, or it might be masking the problem we dealt with later, you know, swapping the, you know, fitting the 100MHz crystal and divide by 2. Now I tried underclocking it, going back down to 48, and I get an error now at 48 now. It doesn't detect something. I think it's like the line RAM. I've got line RAM in the brain. It's the RAM I think it has a problem with. And we had that problem when it was at 25. Right, all back together. Oh god, it was a mess. Let's switch it on. See. Hang on, I've not got the LEDs connected ever. Switch it on again. Power LED's on now. Have a look at the IDE. So it's booting. Right, it's booted up. That's just RGB. So the next thing I'm going to do, now I've done that, is test it on the other monitor over there. Yeah, it took a while to work it out. It was the CPU. Even though these CPUs I've got will run at 50. Not on here, and I think the timing is so tight, you know, performance is really good, and I think it's just pushing it too hard. So you need a CPU that is properly rated 50, not like one of these black top ones that I've got that are plastic bodies that are Mark 33 or 40 that happen to run at 50. Because as soon as I put heatsink on there, it's solid, it's just solid. I experimented with freezer spray, freezing the things around it, you know, the CPLDs, the GALs that is, the FPU, the ASIC, I can't remember what it's called now, the manufacturer of that, you know, the main custom, it's 50MHz rated part. That didn't seem to make a difference. When I sprayed the CPU, I'm like, well, it seems a bit better. And then it warmed up after a minute or two, and it crashed again. And started, you know, boot looping. As soon as I put a fan over there, oh, suddenly it started booting properly, and it's on, it's solid. And that would make sense, because when I did this video, it was like back end of the year, a few years back. I think it was last year I finished it, but it was like around Christmas. It was freezing. You could see your breath in here. I was having to have the heater on all the time, which is why it was so darn stable, because it was so cold. We're now in May, when it's well, it's pretty warm. It's warm today. I actually don't really need a jumper on or anything. Certainly don't need the heater on. But anyway, that seems to be the issue. So I'll get myself a purple ceramic top, 50 megahertz rated one, I think. I may even investigate fitting some sort of slimline fan in there. The other problem is, obviously, when the floppy drive's over the top of the CPU and you've got a heatsink, you've got a tiny little bit of clearance. You can argue the heatsink makes things worse. But anyway, it's running, and we got scan doubled video there. One thing I did notice putting test kit in, it kind of looks a bit strange in test kit. So it's something bespoke to that, you know, something specific to that resolution that test kit uses. So I need to do more testing there. But the only other issue I've noticed is what you're already aware of. When you're in interlace mode, you've got like some stuff at the bottom, at the very bottom of it. And when things pop up, they kind of flicker just a bit. So there's something not quite right there. But, well, for most games and things, you know, it's converting when it's upscaling from 15 kilohertz to 31.5. It seems solid. Yeah, I'm going to have to get a number of other games running on this and just test different resolutions and things, you know. Maybe even switch it into NTSC. Right, so at this point here, I'm showing you some of the photos. I didn't film much of this part, but it wasn't a lot of work. This was like day 3. By the end of day 3, you'll see it was pretty solid, but we still had 1 or 2 outstanding issues, namely in interlace mode. But I very quickly on day 3 got progressive working. Progressive, when we tested in the previous video, you saw that it just goes all over the place. The image, it was just like scrolling around, you couldn't see anything, you could see bits of bubble bobble and the things we tested there, Devil's Temple. And ultimately, you know, I went back to looking at Amber, because what we're dealing with Amber here, you know, the control signals on Amber, the field pins in particular, field 0, field 1, field 2. And there's the, you know, that's where there's a difference between Mattias's implementation, where he was controlling pins on an individual basis for the resets of the clocks and things like that. And the Commodore didn't. Commodore used the flip-flops, and, you know, we ruled out the 14 megahertz in the previous video and came to the conclusion that's an inversion of the 14 megahertz. And that was, you know, the end of the previous part, so that improved things a little bit, but progressive still didn't work. And after digging into the field pins, one of them was still not quite right. And I'll show you the code in a little bit so you can see how I wired it. But ultimately, I'd missed something there. Something was just completely wired to the wrong place. And looking how Mattias implemented it on the AGA Multifix, I went, oh, hang on a minute, I've got the wrong index. You know, he's got like an index for, I think, read enables and write enables and things, and I was just pointing at the wrong chip. As soon as I corrected that, we got progressive. And from there, I implemented scan lines. So, you know, I'll show you 1 or 2 pictures here and a few bits of footage and stuff. You can see as I was testing this, sharing it with the people on Discord and stuff. And I made some amazing progress in that 3rd day. But at the end of the 3rd day, we still had an outstanding problem, and I'll show you the screenshots here of this, where in interlaced, the bottom of the screen was missing off, you know, missing a number of scan lines in one frame. And that drove me nuts for about roughly a week and a half. But there were also a couple of other issues, which I'll talk about as we progress here, to do with sampling and stuff. Right, in the world's smallest space here, one of the final issues, to avoid a massive redesign of this, trying to fit buffer chips and things on. The RGB levels, now I covered this in the AGA Multifix, I think, in a few other videos where I've talked about the resistor ladder used in the hybrid. Now this is a replacement hybrid. It's one of the ones from Suco Pera. You'll have seen this one on my channel before. This was the one that was almost assembled. The other one we tested in that video there, I'll leave a link up top right. So he kindly recreated the hybrids. Now I've got some of these ones from Kavanos. He sent me 4 of these that were, I think they were already, yeah, they were pre-assembled. I just added to add the strip here. So the point being here, coming back to Marine, the Re-Amber, its RGB levels are based on 3.3 logic levels from the CPLD. There are a couple of schools of thought with that. You could pull up the signal to 5 volt, the output. Problem is clamping diodes that protect a 3.3 volt device like that. They're going to be in reference, tied to, the ground and the 3.3. So as soon as you start pulling up to 5 volts, you engage the clamping. And whilst it might work for a period of time, ultimately it'll probably kill the chip. The point is though, because we've got the hybrid here, we can actually address it on this custom hybrid. We can change it. We can just do a tweak, change 3 components on here to bias the transistor. I'll stick a little diagram up of what I mean. Bias, instead of using the 470 ohm, and that's what's on here now, I've just measured that, we can change that to 330 ohm and change it by approximately 25%, which is near ballpark. It's in the field of it should look pretty much the same as it does with the being driven at 5 volt levels, if you see what I mean. I think, because it's just biasing the transistor. So I'm going to remove the 3 470s here, which start, the first RGB input is from pin 1 here, it's pin 3 is the first RGB input. There's a resistor connected to that, 470. There's one over here, 470, one over there, 470. So pin 1 was towards the bottom, so pin 1 is here. So let's now try and squeeze this in here with all these wires in the way. Yeah, this screen never gives a very clear display compared to other ones. It does take a while to boot. Well, we've got video, and that looks a lot better to me actually. The colours look stronger. The blue here and the blacks, even in the white, just looks stronger. Yeah, so I didn't show it, but I spent some time playing around with the PAL line RAM. There is a problem. It's like the alignment's all over the place. I've penciled in JP2 for that in future, maybe, if I can be bothered to revisit it. I just need to double check the RAM that's on here versus my 3000 board, and just determine if they got the same RAM. 42101C-3, 42101C-3. It should be alright on here. So you know what, I'm just going to leave it at that for the moment. I don't even think the PAL machines have PAL line RAM. I think they have NTSC line RAM. I could be mistaken on that, but I think Commodore just went with the same chips, because otherwise, if you think about it, I could be wrong. I was going to say Amber would need to be aware of that. In any case, I'm not going to worry about it for the moment. I do need to test this on NTSC, switch the, kickstart into NTSC. So I need to get rid of this fan now. The fans have arrived. Let's just pull it out there, it was just wedged in. Yeah, I'm going to go and get a sticky thing and stick this down, I think. Obviously I can't stick it that way. What I can do though is stick it that way. And there should be enough space, so we'll give that a try and see if it's any more reliable. It's going to be very tight, in fact. What I might need to do is the metal plate that comes here is just cut a little section out of it. I might do that with the hacksaw to give that fan a little bit of clearance, otherwise, well, it's not going to fit, is it? Switch it on. The fan works. It's pretty silent, that fan. Now, I know what you're thinking, is there enough clearance? It sits on a lump, so it pulls air in, if you like. Trying to show which way it's going. I think it's going downwards, but yeah, put my fingers around the sides, I can feel a breeze, because there's a little gap around the outsides of that fan, if that makes sense. So this second one, I need to remove the chip from that. It's got the 9572. I'm going to remove the pins as well. I'm just going to remove everything from it. I may reuse the board, I don't know, for the one I'm trying to build here. Don't underestimate how hard it is to get pins out of a board like this. I've spent a couple of hours, I'm listening to my mate Vincy while I'm doing it. It's past the time listening to him. So you sort of had to relocate that cap, I fitted it in there, everything's connected up. This is the first test. Please God let this work, so fingers crossed. Bear in mind, the firmware for this has got the firmware's got progressive scan lines, so we should see some scan line action if it's working. Oh, hang on, we didn't see no sync. You can't see the LED, the monitor's on. The screen's black. Oh my god, it works! There you go. And I can see the scan lines. That looks fantastic. It looks so much better when you've got scan lines with progressive. It's anti-aliasing for the optical part of your brain. That's what it's anti-aliasing. It's like your brain fills in the gaps and everything looks rounder and smoother and the colours and everything blends better. That just looks incredible. Bear in mind, I've not got the modified hybrid. If you wanted to get this a tiny bit brighter, like 20% brighter, you'd need to do the modification I did to the hybrid. That's incredible. So the problem I've got now is I don't know why the Mod 3000 is not booting from the SCSI. It was working like last time I used it. I don't know, I've got something that I've forgotten about, a jumper or something, I don't know. But it's working. Woohoo! Right, I'm calling it there for the release firmware and PCB revision. Obviously I haven't got the final revision here, so I'm going to order another revision of the PCBs and we'll do one file test with the file version. But that's how I'm going to leave it. And you can see progressive there with scan lines on. This particular firmware I've just forced the jumper to be set to get scan lines. And interlaced looks fine. It's stable. It's harder, it's definitely harder to dial it in than maybe on a real amber. And my advice is to replace the 7.4 ALS 7.4 with a 7.4 F7.4 just to get it looking a bit sharper. But I think that looks amazing, and it's stable is the key. Yeah, I think that's looking alright with scan lines. And the exact same firmware on the other chip running on the GBA1000. And as you can see, it's looking pretty good there. It's not got scan lines forced on this one, so scan lines are off. That's progressive. Let's just wait for it to actually show some more video. There you go. I think you'll agree. Looks pretty darn good. We've got no flickers or speckles. It seems alright. So yeah, I just need that final board revision, but I think the firmware is going to stay as it is there because it works fine with the GBA1000, it works fine with the 3000. And as I said earlier, if it doesn't work for you, let me know, but don't expect me to fix this. I'm not selling this. This is open source, and if I can resolve it, I'll try and resolve it, but if I don't have the hardware and stuff to replicate the problem you've got, then I won't be able to. But it's open source, you can have a go yourself. Yeah, very pleased. And the final rev I need to do to the board before I order another lot, and I've got to thank TRU again. He sent me a donation that was just enough to order the second lot of PCBs here, which I'll build in a minute. But we need a third revision, subject to change. It's a release candidate. The only outstanding issue was the switch here was not working. When you switched it there, switched it off, it bypassed RGB through, and you can see on my monitor down there, it goes, 15.6 kilohertz, can't support it, and then you switch it back, and it'd stay on 15.6 kilohertz, and I'm like, what's going on here? I spent ages looking at the code, and I tried a few different things, and I couldn't fix it. And then I started to think, maybe the weak pull-up is a bit weird on these. Maybe it's like a capacitive type thing, where it's, it's pulled high by a capacitor as default, and then you pull it low, discharges the cap. Pull it high, well not high, put the switch in the other position, stays the same, because the cap doesn't charge back up again. And I think that's the case. It may do over a period of time, it's something like that. It could be a MOSFET that's doing it, and for some reason or other, because it's not detecting actual high, it doesn't go back to high. So I've just bodged a resistor on here, on the switch pin, across to the JTAG 3.3, and I'll show you it works. But it's incredible how long that took me to work out. So I've switched it over. You'll see it goes 15.6 kilohertz out of range, and the RGB should be passed straight through. Obviously, this monitor can't support it. I need to move the 3000 over there and test it on the other monitor. And I switched the switch back. Now it's actually working. It does go back, so I'm very pleased with that. I could do that final mod to the PCB and order what I think is going to be the final revision. Yeah, so I will be sending out, maybe even selling, at cost, these prototype PCBs, because I'm going to have too many to give away, and I'm not going to be building any more for my own use, I don't think. I've scratched the trace there, that's 3.3, and then I've just got resistors I had here. I've got a load of these 8K2s, which were precision ones for that Dell Pentium 3, when I thought that maybe I needed to replace components. So I've got to stick this there, hang on, if I can get it in position. Let's just get some solder on here first, and then I'm going to try and join it up there, and any of them I send out, I'm going to send them out with this modification on there, and any other modification, like the first rev, for example, need a cut trace, and I'll do that, I'll cut the trace, and they need a couple of wires, those first rev ones, but if anybody wants to build one of the first rev ones, they can, and it works. It just doesn't have the jumper, and it will have a couple of modifications done by me. It's just a way to not throw them all away, really. I don't want to throw them away, I don't like throwing things away. Like I said, no warranties, no guarantees. This is working for me on my 3000 with a few mods, and it's working on the GBA1000 as, you know, built. So, yeah, will it work for you or not? I hope it will. Switching it off, there you go, 15.6, switching it back, yay, resistor works. So we tested the prototype already. This is the Boto type, this is the one that's marked Boto, the second one that's got jumpers but lacks some of the things on the release candidate version. I fitted a ferrite on there for the 28 MHz clock to go in a 3000 because I think that's where it's going to go, and I fitted the pull-up on the, what's it called, disable switch. The other thing I've just discovered, I'm thinking about it's logical, you need a pull-up on the jumpers as well, so I'm going to need to go alter the board design before I get those release candidate boards done. And the reason I know it needs a pull-up is because you can see we've got scan lines here now. Well, you might not be able to tell from that. We've got scan lines in this progressive mode, and I put the tweezers on the jumper pads and scan lines came on, and I pulled away, scan line's still on, and I'm like, damn, that's the same thing. There is a weak pull-up to start with, it's no longer there after you know, ground it. It will be when it power cycle it, and I'll power cycle it now, just so you can see what the desktop looks like. When I first tested this, it had a few weird pixels in the middle here, but I think that's actually the RAM, it's actually frame RAM or line RAM. That's probably frame RAM, I would think, that was playing up. Bear in mind, this is, yeah, it's not doing it now. They were here, there's like a bunch of pixels here, just like hovering, staying there. And I power cycled it, it went away. But I think that's my, like I said, the RAM. I think it's the frame RAM or the line RAM on this GBA1000. But it's solid. Ignore this blue thing here, this is the screen. It's fine. So perhaps not quite as sharp as a real amber, but, well, beggars can't be choosers, so I'm happy with it. I'm more than happy with it, really. It's now going to get ultrasoniced, and it's going to go over to TRU. The only reason I'm sending that to TRU, fully assembled one like that, is I think he's ready to plug it into his 3000 more or less, and he's given me 2 different donations which are paid for the 2 different prototype batches, and he didn't ask, but I just figure he can be the first test guinea pig. He's in the UK as well, it's easy to get it to him, but the other ones will go out very soon after this. As I say, I wish I had a CPLD to stick on every one, but I don't, and it's taken me best part 3 hours to make that, and I was stuck with one issue that I was aware of and one that I wasn't. I'm going to show you those now. I'll go back through the code, explain some of the code, and explain how I got to the end result here of everything working. But you can see everything set up here. So I just left it like this way, you know, used it this way with the JTAG constantly connected, constantly running. It did highlight a problem with the GBA1000, and that caused me some really annoying problems at the start. For the first day I was developing the code. The other thing here at this point, and we'll come on to that in a minute, I've got a custom hybrid in here now, just to bias the RGB sufficiently to take into account the difference between 3.3 volt logic levels and 5 volts going into the hybrid. So it's an easy thing to do. If, you know, you can argue why don't I fit that on the Amber, but it would mean fitting 2 4.5s on here effectively, you know, at least 2 of them, because we've got 12 colour bits. Try and fit that on that little PCB, it's impossible. even with the tiniest little BGA type ones, I think I would super struggle. Certainly on the 2-layer, it'd have to be changed to a 4-layer board. It's a complication that I just feel unnecessary. So you can see the hybrid here. I just customised that hybrid. There you go, problem solved. So anybody who wants to fit one of these, if you're going to go to the hassle of fitting one of these, and I don't even know whether I'm going to do a PLCC plug for it. I'll think about it. I might try and do one where the PLCC plug fits into the socket and then this plugs into the PLCC thing, if you see what I mean. Because that would be a way to potentially achieve it. I'm just not sure whether the pins are going to be, I think they are, the pins are going to be in the place where the plug is effectively, so I'm not sure that would work without another interposer, an intermediate PCB in between to move things around. Bottom line is, any machine that's not got one of these, if you're building a GBA1000, yeah, just solder one of these straight on, yeah, and fit the relevant hybrid. The same thing holds true of, say, a 3000. If you've got a 3000 and you haven't got an Amber, just remove the socket and fit one of these, and at the same time fit a custom hybrid, and then everything's good. Yeah, these parts are going to be more reliable than the things, the old parts anyway. So is it really a big deal? Probably not. Yeah, so I'm launching the VM here. I've just double clicked on that project navigator, and the way I went with this, I installed ICE 14.7, and I was pleasantly surprised when I installed it. It created a VM, a virtual machine. You can see the virtual machine here starting up from a save state. And it's incredible, really. So yeah, I've commented it all up at the top here. Originally we started off focusing on the XC9572XL. I'll retest it against that later. I'm not sure whether the code will just fit in it or not. It might not do with the jumper option that I added for scan lines. And I may just have another look in a minute to see what we can use JP2 for. I was going to add another feature to indicate are we in progressive or interlace, by changing the top, I don't know, image, part of the image, the scan lines, so many pixels, or like a square in a corner or something. I don't think there's enough space to achieve that, and I'm not sure it's really required. You'll be able to tell if the jumper's on and you've got scan lines, you're in progressive. It's that simple, so it's a bit of a pointless thing. And what I may use JP2 for is potentially speed difference between PAL and NTSC line RAM. I'm going to put some PAL RAM back in it in a minute and test how the alignment looks, and if the alignment's off, I'll use JP2 to tweak that so it looks right. So just having a scroll down here, you've got some includes basically type things at the top here, where it tells you define what kind of logic libraries I guess you're using. What else have you got? I declared all the stuff here, so we've got 12 colour bits, and you can do these as buses, and I'll explain that a little bit more in a minute, rather than separately, defined here the way I have done. So you've got 4 bits for red, green, and blue in, and then we got that's 12 bits, and then we've got 12 bits for output, which go, as I've commented there, to the DAC, the hybrid. In our case, on the AGA Multifix, it goes to a custom DAC. Specific DAC, and then you've got RGB. I've called it delayed. I assume it's delayed. It's referred to suffix or prefix with a D on the original 3000 schematics and on the AGA Multifix schematics. And then you've also got 12 colour bits for combined. Is it really combined? I don't know. It's got a suffix, prefix, and C on aforementioned schematics. So you can see we've got a lot of blooming colour bits coming in and out of this. That's one complication over the AGA Multifix, because the RGB was just kind of all directly routed to the right place. It didn't go in and out of anything on the AGA Multifix. And then you've got your syncs, inputs, clocks. We've got 40 MHz clock, 28 MHz clock. Bear in mind that 14 MHz clock is PLL synchronised to the 28 via the trim cap and stuff and the PLL circuit on the 3000 and in the GBA1000. So it operates just the same as it does in the original thing. You've got the switch to bypass, that's here as well. I haven't tested that yet because you can't bypass it on the GBA1000, but we'll test it on the 3000 soon. And then some of these things obviously were predefined from the original project, read enable, write enable, and then you've got reset for writes, reset for reads and reset for writes, got those around the wrong way. And then VSync and async out, those are going to be in reference to the 28 MHz clock delay. It's going to be scan doubled, isn't it? So, if your VSync is coming in, one of your syncs is coming in and it's at 15 kilohertz, it's going to be 31 point whatever on the output. It's doubled. And then I defined these things here as outputs. And I've changed these so that they match the names on amber, and tried to comment those as well in places. And we've got R2 jumpers. And then as I continue scrolling down here, now this is an interesting bit. You know, I might get some suggestions here on how to change this, because this was my first time playing around with VHDL. Well, it didn't compile to start with, you know, and the way you compile it is you go onto the thing here and you right click on the design implementation bit and you do run all, and then it just runs through these things. It synthesizes it, translates, does the fitment part, generates the actual JED and stuff, and hopefully you might get green ticks or maybe an explanation mark or two, which is just warnings. If you get any red crosses, you've got a problem. And the errors come up down here, and that's something I'll just sidestep to and just explain as well. It's like all software, there are bugs in it. There are bugs in this 14.7 version, and it caused me some stress towards the end of this project here, where it would go all the way to the fit stage and then give a red cross in the fit, and you'd look at errors and it'd be blank, and I'm like, oh, thanks for that. Thanks for giving me an error and stopping dead in your tracks and not even telling me what's wrong. So that drove me nuts for a while, and I googled the heck out of it and found that, I think it might be on the fit stage, you go process properties and it's on the reports bit, able, change that there, HDL equation style on the reporting, yeah, you change that to able, because I think originally it was on VHDL or source. That's what the problem was. As soon as I changed it to able, it was alright now it can fit it. So that's the reporting side of this. It's got a bug in it that means you can get, you know, a false, you know, a fake fail when there's nothing actually wrong with your code or the fitment part. So anyway, things like that I had to overcome. Coming back to what I was saying here, so I created shared variables here for each of the 12 colour bits, and the reason I did this is this acts as an intermediate location, if you like, to plug the various inputs and outputs. These buses, we've got 4 different 12-bit buses. Now, logic says you'd think it'd be easy to have a little bit of conditional logic that says, you know, if such and such join the, you know, the input RGB bus, all 12 bits, to the output RGB bus, and just check, you know, have that logic change, you know, almost like a case statement type thing if you're a developer, to say, you know, depending on where we want to look, which 12 bits are we pull into the output. Yeah, it's not quite that simple, because you'll see as I go down here, if I just go down to the implementation bit, this is where initially I had some code here, you know, to set the outputs, yeah, to, I don't know, let's say the line buffer a delayed output when such and such a condition. But then you've just got else, you've got either or, one or the other condition. This VHDL statement here seems to be, and I can't seem to find a way around it. I did search on case statements and things like that. You don't seem to be able to have a multiple condition set of, say, sources going to a destination, you know, for each one with a different condition. That doesn't seem to be something that's easy to do. So someone who's masterful at VHDL may be able to come up with something that's really easy there. I couldn't find anything, and bear in mind I've had no training on VHDL. I've never looked at VHDL before. Other projects I've looked at are very long, and you know, I'm more familiar with that because it's very similar to C++, etc. And this has got more in common with, is it ADA? I think it might be. It's like Delphi syntax, some of it. You know, some of the assignment things, the colon equals is a Delphi thing. So anyway, as I dove into this, it was obvious to me straight away, you know, this is like your wire statement. You're saying that the red out is 0, first bit is you know, going to be wired to R0, and this is where I created a variable here, when whatever your condition is. And then, so what I've done with this, why I've got this shared, you know, these shared variables, it's like I say, it's an intermediate place for the inputs and outputs to connect through. Now, I've done that in what I think is a fairly clever way, because I can only have one statement here of, with you know, in the wiring the inputs to the outputs. I've decided to have it to, you know, the main buffer, yeah, the output comes from the main buffer, this shared variable, that's what all these are down here, all these 12 bits, when the black pixels are off,
Yeah, don't assume that means that it's the colour pixel. It's not. It's just a boolean I've used to say when you've got black pixels, e.g. scan lines, or blanking, you know, at the top, you know, before the image and after the image, you know, after the H-sync at the sides, etc. When you've got that, then we set zeros there, yeah? So that gives us scan lines, it gives us the black part for the, you know, edges of the screen and stuff, top and bottom all around. Or the buffer gets passed to the output, and then further down in the code, the point where I want to actually connect things up, it really is as simple as making sure that I have the relevant logic to make sure we don't get contention. So, you know, in other words, looking at the output enable of, you know, given line RAM, and if that's active, it's low, then connect our buffer to, you know, the relevant input from the line RAM. Yeah. As I say, contention is something you've got to think of with things like that. If some of these overlapped, you may find strange things going on the display, and I might be able to evidence that. You can do that. If I was to try and you know, fudge the I don't know, scan line output so that I maybe stick a colour, if I try and force a colour red over the top of the red bits, you know, ignore that, you know, override them with a fixed value or something, you get weird things on the display because it's actually doing it. It does what you tell it to do. In other words, it will feed, you know, if I say feed 4 highs into the first 4 bits in red, yeah, regardless of what's going on with this output enable here, it will do that. It will connect them both up. You'd think it'd be intelligent enough for the, I don't know, the synthesize or fit position, you know, section to go, I'm not going to allow that. You're going to get contention. Are you stupid? You know, but no, it does. It allows you to do that. And you can get some really weird things going on if you get contention issues. So you've got to make sure that the conditionals for each of the, you know, each of the places here where I'm feeding 12 bits all through my buffer to the output. You've got to make sure you don't overlap. You don't have 2 devices, 2 line RAMs or otherwise writing to the same bus at the same time. But that seems fairly easy with this because, you know what, the AGA Multifix code was pretty solid, and the output enable timing seems absolutely spot on there. There are no overlaps, so don't even need to further qualify the conditions there. And that's something else I'll come on to as well, is the conditions that you use here. There's a time delay. There's a time delay associated with everything. You know, you think of C# and C++. There's a time delay with that, but you don't really notice it. You notice it here if you had one extra condition on there. If you were to say if blah, then, you know, and then put an else statement, because you've got 2 conditionals here, you end up with, you know, think about the logic. You know, you've got an or an and or something comparing bits to, you know, as your logical condition there. You'd have one above it as well. You've now got a delay. You've got propagation. You've got propagation from adding an extra conditional. So there was a little bit of that early on where I'm like, nah, I see what's going on here. The more complex I make the logic, the more balked the timing gets. Yeah, and obviously this is a very fine-tuned in terms of timing thing, the implementation. And let's just talk about that for a while. If I go back to the top of the project here and have a look at the stuff that's, you know, predefined in this, 95% of the code here, or maybe not 95, 90% at least of the code here is thanks to Mattias Heinrichs and his absolute amazing grasp on the timing required to get something like this working. So you've got everything, you know, he's counting pixels on the input, counting pixels on the output there, lines, counting lines, all sorts of Boolean stuff to do with H-sync here. Are we in what phase of the H-sync are we in? Are we in V-sync, etc.? So, you know, just sort of control signals and things that you might expect to need to use if you're trying to track where are we? Are we in H-sync? Where in H-sync are we? Are we in V-sync? And then, of course, you know, in the TV mode, PAL or NTSC, are we interlaced? Are we not interlaced? What frame type are we in? Is it you know, what type is it? Is it the first frame or the second frame or the first line or the second line? You know, in even frame and odd frame, those are the sorts of things when it comes to interpreting interlaced video. You're going to need to keep track of those things at each point in the stage. And then it's got some defaults here to initialize the resets and writes, reset the reads and writes on the various types of RAM there, the frame RAM and the line RAM. Read enable signals, write enable signals. Are we blanking? Is it blanking a line, etc. And then lots of stuff here, constants and other things that work out. What we're doing here. What's the scan line width in PAL and NTSC, etc. There's some of the things I just talked about: PAL, NTSC, even, odd, progressive, interlaced. But this stuff here is the mathematical side. You need to know exactly how many scan lines you're dealing with, frequencies of things, and then some slightly more complicated things to do with timing of H-sync, and this is the stuff that there's no way I would have worked this out. I'd have been at this for like 2 years. If this project didn't exist, the AGA Multifix, it would be like, Gadget starts the project, 2 years later, Gadget's tearing his hair out of trying to understand some weird H-sync timing issue coupled with a V-sync thing. It's like, and then I may have fixed it. It might be like 2 years of work for me to do this easily, because I'm just not that smart. It would be. I could do it, don't get me wrong, but it'd be a little bit. You've got to do a little bit, a little change, understanding the problem, overcoming a problem, etc. So you know what? All the hard work has been taken out of this, including things like that H-sync pulse width. How on earth did he come to that conclusion? I don't know. He must have looked at definitions of H-sync and video standards, related to the Amiga. Maybe he scoped it, maybe, I don't know, because he's got this value here. It's got to be between 30 and 65. That might fit within standards. It might just be an Amiga thing. It might be a standards thing within monitors, what they're most comfortable with, and he's gone bang in the middle there roughly. I don't know. Where did that magic number come from? That's the sort of thing that would take me 2 years to work out, probably. And stuff here that I am aware of, but again, I wouldn't come up with these values. H-sync front porch, back porch, the H-sync signal, in simple terms, and this is where my brain was before I started this project, I'm thinking, H-sync, it's just a pulse, isn't it? What's hard about that? V-sync's just a pulse. It isn't. It's a pulse, but it's It's a structured pulse. But when you actually look at it, you have a front porch and a back porch that, one leads in and one trails, and they've got to be the right voltage for the right period of time. And if you don't get that right, all bets are off. So there's some complication there. I'm aware of that from a composite point of view. And when it comes to RGB, I honestly didn't think there was a front porch and back porch on these things, but there is. So again, that would have taken me years to work out. And you can see there's a lot of different, constancies defined there to do with the timing of that. It's incredible. Hats off to Mattias Heinrichs. Hats off to him. And same with V-sync. And then some timing for the memory here, the field memory. Again, some of this stuff, I wouldn't have been able to work out easily. If you scope things and logic analyze, that's where you can work out some of these timing things that you need when you look at the original AMBER. And I'm guessing that's the sort of thing that Mattias may have done when he was looking at this in respect to the AGA Multifix. So one of the early problems I had was, in fact it ended up being related to the final problem. He had 128 defined here in field mem write reset for PAL and NTSC. And that was, I'll show you what that does now. This is where, within the first day, I was at this point, I'll show you, where I'm like, oh my god, it almost works. And that's the thing, almost. There's a big difference between almost and does actually work. And I've had to get into this routine of going to and from to delete. Hang on. Is that even doing anything? What's that doing there? That's rerunning. I have to occasionally zip off and delete the source code from my Win 10 machine here. Obviously I'm loading impacts here because I haven't got impacts up at the moment. And I just leave, let's say, the Amiga on with the JTAG running. I disabled the USB on the VM. I'll explain why this. I can't find it now. The thing's not there, is it? In this VM, it will. You can use impacts on the VM via USB on your host computer, it was just painfully slow. If I tried to use Impact on this VM here, it would take 10 times longer than it would to do it on the Windows 10 machine. I don't know why. Is it because I was sharing the USB connection and there's some sort of polling delay thing or something? I don't know. I'm trying to copy a share to itself. Yeah, so anyway, I had to do this. I could have automated that if I'd have done a little bit of scripty sort of stuff in Linux, probably. What's it called now? Share. Marine. Here we go. Program. Here we go. I think it was, yeah, trying to connect. So you can see we've got an overlap here. Now it's interesting because I've changed some of the parts of the code. The overlap is not where I thought it was. It's here. So yeah, I fixed a bunch of things. That means now when it's 128, it's over the left-hand side. I've got this theory that when I put PAL-RAM in there, it might actually work. Actually, that's what maybe all that 128 will assist with. I might need to change the 128 to something else. But anyway, you can see the immediate issue there. And you know, the first thought is, why doesn't that work? You'd think it should. If you look at how the AGA Multifix works, it uses the same RAM, uses the same line RAM, and that's, you know, a complication as well. That whatever he's doing in terms of his timing is just subtly different to the way Commodore did it with the Amber. Amber is using a 7/4 flip-flop to, and I'll show you the schematics here, to control the resets. I think one of them is actually influenced by a signal that comes from Amber, but you know, the resets and the reads and writes, you know, the read and write enables effectively on the frame RAM. And I think that ultimately that's the issue, is like one of those two implementations, either the AGA Multifix or the Commodore approach, is faster than the other. One of them is faster than the other. One of them, the timing is different to the other. But, well, it's such a small amount that it doesn't break anything, but it does when you just try and put code from one place to the other. You know, you need to make a timing adjustment. Yeah, so going back to the code again, yeah, that 128, one of the first things they did is went, let's try changing that. And I was surprised when it moved the picture even further. But it, you know, it almost aligned it, but I'll show you what it was doing. And you know this because you've seen the clips earlier on. But if I just change some code somewhere, if I can find it. So this was my fix, final fix. And I'll explain that in a minute. So this is the code back as it, hang on. Oh, here we go with cryptic things. No, we don't, it's just got a missing bracket, that's what's going on there. Yeah, sometimes the errors are really cryptic, it gives you. Other times not so much. Hang on. Then. Oh, we got two brackets somewhere. Oh god. Yeah, it's really easy to mess up the logic. It's the brackets. I've got like a few different things in that. You know, a few different conditions. And the brackets are messed up by commenting out at the end of it. So we'll just change it to a 1. That'll give us pretty much the same behaviour. And 41 is not how I need to leave it. And that was just a reminder to me that's something I need to change, and we can review that now. Yeah, so this is where we ended up like 2 or 3 days ago, where I'm like, oh my god, it's so close to being perfect. You can load a game, you don't get this issue, everything was fine. So the chips, you know, that relate to the, I'm trying to think which side it is now, the C side, the C suffix prefix line RAM, fine, no issues there at all, no timing issues, everything's fine, full screen displayed, doesn't matter what resolution it's in, always works. In interlaced, we had this going on, and I spent blooming over a week trying to work out what this was. Bearing in mind, we were nearly at like 95% completion after 3 days. So after 3 days, we're in this position where pretty much everything was solid. This is what took me 90% of the time. I spent over a week, probably 1.5 weeks, trying to work out what the heck's going on down here. Now, there were a number of people saying it seems like your frame RAM is filling up. Yeah, your frame RAM's full. So I spent so long stepping through various tests to try and determine at which point it was going wrong. You know, and looking at the logic, comparing the 3000 to the AGA Multifix, looking at those flip-flops, tweaking the timing on code related to those flip-flops. I must have spent 3 days messing around with just that. before I start to look at other timing within the code, the things you've already seen, like changing the H-sync pulse, changing the V-sync pulse, changing the delay statements in there, changing the code that says, you know, start to use a certain buffer, you know, output enable when, you know, you're so many pixels across, so many lines down. I tell you, I went through everything. It's like there was literally nothing left, and then I just got this brainwave. I'm like, there's a statement there for an output enable that says if we're in H-sync. What happens if we change it to if we're not in H-sync? And when I did that, everything changed. I'm like, oh my god, hang on, that's giving me a huge clue here. What happened was, when I changed the H-sync statement in the bit of code you've just seen me modify, what happened was, we didn't have this, yeah? What we had was a perfect screen, but it was the wrong screen. It was the next frame, yeah? And that gave me a clue. I'm like, hang on a minute, it's almost like when we have that condition to say when we're in H-sync, the frame we're in has this issue. But when we say we're not in H-sync, we're now coming out H-sync, we start to get the next frame, and that frame's perfect, which means it can't be the frame buffer that's filling up. Maybe it's something to do with, you know, it's trying to output each scan line, H-sync kicks in, oh, the code automatically switches off the output enable. The output enable's disabled at this point. Now, that's the first thing. So then I show you an image here. What I tried to do there was, I left it in interlace mode, I disabled the actual line RAM that we're seeing here that's given us this issue at the bottom, and instead, when the output enable was low, you know, it's active, that line RAM, I just drew red pixels, and you can see on that image, it's pink, and I'm like, well, the output enable is fine. It's not like there's a problem with the output enable. That doesn't make any sense. But then I still came back to this H-sync thing, thinking if it's not the output enable, then the line RAM, the frame RAM is being shut down. You know, in other words, it's not feeding across. The frame RAM is not feeding across to the line RAM for these scan lines because of that condition. The H-sync's stopping it. The H-sync's going, no, that's it, we've got frame. No, we haven't finished. Yeah. So looking back at the code again, the final part of the puzzle here with this, and I'll show you some more problems I had in a minute. The final part of the puzzle was adding this bit in here. Yeah. I'd already proven if I set when I said H-sync before, we're talking about V-sync or H-sync. When I changed it to 1, we had a full image. So like I said, this is why I then, you know, I had a further condition here to say the alternative, you know, when we're passing the, you know, the data from the frame RAM to the line RAM is, well, we've reached a V-sync, but hang on a minute, let's just allow it for so many lines on the VGA output, you know, additional lines, so that we can continue feeding that data and not cut it short as we're doing at the moment, and that works. So this is why we've now got this set to 1, we have the original problem. It's almost like this whole statement is not there. Now this is where I need to experiment, because you know what, I had 41 there, it doesn't need to be anywhere near that. I'm just going to set it to 20 and see if that fixes the screen. And I may start reducing it 1 pixel at a time. I'll report back in a minute, because you don't want to see me do this for every single you know, reiteration of testing this code. And I think I'll just show you progress. So that's with 20. So now we're half as much, aren't we? So you know what, 40 is not far off. There must be about at least 15, 10, 15 there. 40 is probably too many. Anyway, I've set it to 30. So I'm now going to copy the code across again. Can't be far off now, maybe 5 or 6 lines. Yeah, look, I could zoom in on my phone there and actually count those. That's what I think I'm going to do here. Yeah, this is the scientific way of doing this. It's harder than you think, because you get the interlace stuff going on when it's flickering like that, so you can't see what's a scan line and isn't the scan line. Let's try 6. I think there's at least 7 or 8 there, but let's try 6. And this is the other thing, you know what, I'm simplifying this stuff at the moment. You're seeing how simple this looks, and trust me, it wasn't simple at all. Because what you don't realise is, whilst I was doing this, I had KiCad open, I had the 3000 schematics open, I had the AGA Multifix schematics open, I had the pins file open, there was like 2 or 3 other things, including impact. So like, you try and juggle all those things, alt tab, alt tab, alt tab. It was like one of the most stressful things I've worked on in months. It made Cathar's A3000 repair from hell look easy. if I'm honest. And that's the thing, you may think this has been easy. Yeah, the first 3 days were easy, the rest of it wasn't. There's so many, and there's lots of small issues that I'm not covering here in terms of, me showing you the fix. There we go. Hang on, I haven't deployed it yet, have I? Yeah, there's lots of small fixes I've done. It's not just been 1 or 2 things, it's been half a dozen. So yeah, don't assume that that's all there is to this and that I've had a really easy time with it. Even just doing the pin-out stuff, mapping pins. You try doing a project like this, taking on someone else's work and then trying to map, 36 different colour bits that aren't on the original project, and then try and adapt where the logic's very different in terms of the output enables, the resets, etc. And see how you get on with it. It's, it's harder than you might think, is the point. And there was a lot to overcome in terms of, trying to understand VHDL, trying to understand everything about this. Yeah, you see, we're almost there now. We've now got what will look to be 3 or 4. I'm going to put 3 and see if we get 1 scan line at the bottom. I'd like to try and edge up to it, but you know what? I'm up to 39 now. So we were at 41 before. We weren't far off, were we? You start to lose your mind as well after a while. Like this routine. And I tell you what, anybody who says, how many times can you program these Xilinx chips? That was a question I asked a few years ago. I think Stephen was like hundreds of times. I've programmed thousands even. Yeah, he's not wrong. He isn't wrong. I've programmed this chip about 400 times, maybe 300 times. Maybe I'm over exaggerating. But this process like this is, I've been round and round and round, and it still works. Chip still works. It's fine. Still verifies, still programs. It's incredible how bulletproof these things are. So you can see now at the bottom here, I can see we're halfway on 1 scan line, and I see 1 grey scan line at the bottom. So you know what? I had it dialed in perfect, didn't I? It was 41. There we go. So, yeah, I see half a scan line here. Now that is grey. That is grey. That makes me think that can be done. So you know what? I have fixed another bug here that I was not aware of. I was right to be concerned, thinking, I need to check that 41. Is it really 41? I'm going to change it to 42. Oh my god, we do! I have fixed another problem. I'm so glad I went through this little bit of a tutorial thing at the end. We fixed, there you go, fixed that half a scan line. I thought that was just how it is. No, it isn't. You can get the full, very final scan line on there. So there we go, another problem fixed. I'll show you the next issue now. And yeah, this one was it was easy for me to work out, but I didn't notice it for some time, is the point. It took me some considerable time to go, is there a problem there? And then as I did more experimentation, disabling output enables and just looking at the, individual components here, one set of line ramp versus the other, I started to come across a theory. And I had an alignment problem that lived to, when I showed it on my Discord, he was like, looks like it's showing the same scan line. I'll show you an image of that. It looks corrupted, looks totally corrupted. And it was only occurring in interlaced, but that helped me focus on this. And as I scroll down the code here, you'll see we've got the code for the actual output, RGB output, in a process for the 28 megahertz clock domain. The 28 megahertz clock. It wasn't there originally. That didn't exist. The AGA Multifix did nothing with the 28 megahertz clock. And as I thought more about it, I'm like, hang on a minute, this RGB that's going out, Scandalboard, we've got a difference here. We've got RGB. The AGA Multifix doesn't have RGB. So, just maybe, it's not in the right clock domain, which is why I created this. So I could show you how this behaved. If I just cut and paste this whole block here, and paste it into the 14 megahertz clock domain, this is where I started, which is an obvious thing. You just go with what's there. I'm like, well, all the other stuff's operating on the 14 megahertz clock, in reference to the 14 megahertz clock, let's just stick it in there. And yeah, that first day or so, first 2 days I think, I was, maybe even the first 3 days, I was running alongside this, the code this way. And you'll see what the difference this makes. It may give us no video at all now, I don't know, because this is one of the things I was finding, that you can do a subtle change to the code, and suddenly there'd be no video. And I'm like, why is there no video? All I've done is added one single if statement, And that's why. It's because you're adding a delay with some conditional logic and if statement. And if you're in the wrong clock domain, that delay is going to cause you a huge problem. It's going to be difficult enough adding 2 conditions in the 28 megahertz, but 1 you can get away with. But, you know, a few in the 14 megahertz, well, good luck trying to get what your expected behaviour is the point. Because you just knock the timing out. You know, this timing that you might not be thinking is there, and it slaps you in the face. So if I program that now, we'll look at what it does to the display. Don't know what's going to happen here, actually, because the code is very different. Yeah, it kind of looks alright, doesn't it? You're kind of looking, but I'm like, that's a bit square. We've got a square Commodore symbol. This is the thing, and I spent quite some time, an hour or two, looking at that, going, maybe the timing for the, you know, every other scan line is off, and it's like we're getting a zigzag type thing going on. But then the line looks nice and straight down here. But why is the circle around the Commodore square? And then, as I say, this is like on day 3. I was like, well, let's just test some more stuff. And I went into here and I went, I know, let's have a look at sysinfo. You might not do it now because the code is very different in a number of different ways than it was at this point in the video. No, it is. Can you see? It just looks a bit... It just doesn't look right. It looks a bit blocky. It looks a little bit strange. Look at these here. Look at that. Yeah, it kind of looks like a bad upscale, doesn't it? That took me, let's say, 3 days to notice, and then it's like, you know, an hour later, I worked it out. I'm like, I think it needs to be in the 20 in reference to the 28 megahertz clock. And as soon as I did that, and I experimented with falling edge, rising edge, but yeah, as it was a minute ago before I changed it, it was perfect, and it looked horrendous in here. Did you go into AIBB? I mean, this is, there you go, look at that, it looks horrific. It looks horrific. And this is where Live 2 is like, it looks like it's showing the same scan line. Well, it isn't, but what it is doing is outputting things fractionally at the wrong point in time, or reading. It's reading, I think it's reading from the RAM at the wrong point in time. So it's being output right, but we're getting like a sampling issue on an edge, you know, a pixel's just changing state just before it got red. Oh, that one's red, that one's red, that one's not got red, oh, that one's got red, that one hasn't, oh, another one hasn't. Do you see what I mean? Because you're on a different clock domain, yeah? You want to be sampling at exactly the right clock domain. If your output at 28 megahertz, you want to be sampling at 28 megahertz. Well, if your output enables at 14 megahertz, good luck trying to get a proper display. What we've got here is a 50% sampling of a 28 megahertz video signal, if that makes sense, which is why it kind of looks half good. It looks half as good as it should do, because we've got a sampling issue there. That is what it is in layman's terms. You know, if you only look at the data once every, I don't know, 2 seconds, and there's 1 second intervals, you know, your data's changing every 1 second. I'm trying to simplify this here. You know, data's changing, and you're like only looking every 2 seconds. Good luck catching the changes. You won't notice half of them. Yeah, that's the issue. Yeah, I hope that is clear. So coming back to the code, I've got to try what I did now. Yeah, and as I say, just cut that whole section out and went, let's create a new process, and I set up one for 28 megahertz. So what else? Yeah, so I did lots of experimentation on the output enabled timing, the read and write resets. A lot of time spent on the read and write resets. Trying to understand, was that the thing causing me, you know, the issue with the scan lines at the bottom. Coming back to, you know, the start of this project, I've been putting this off. Why? Lack of confidence. I kept telling myself, you know, and having this fear, a terrible fear. Well, I don't know how I'm going to design the board, and then eventually just push through it. When I'm going to do it, I'm just going to do the board, And then when I finish the board, I'm like, oh my god, I don't think I should get this board done because there might be some mistakes on it. I don't think I've got the confidence to go through the board design and work out if there's any problems. And then I pushed past it. I thought, no, just, you know, sod it, order it. If there's a problem with it, I'll fix it. And we've done that. We did find some problems, and that's the thing I did day one. When I started porting code to this, I realised, oh, hang on a minute, I've got 2 pins that are mapped incorrectly here. I need to cut a couple of traces and add a few wires. But the point is, you overcome. You can be put off doing something because you are scared, because, and I am like that, I'll admit it, I was scared to do the KiCad design. It was a complicated board. I was scared to retest it because I thought it was going to be a load of time. I was scared to start trying to install ISE because I thought it was going to mess up my impact on my machine, mess up my machine. I thought I'd then spend weeks and months trying to learn how to use the software, how to create a project, how to get the code in there, how to get it to compile, how to overcome errors, how to map the pins, how to... You see what I'm trying to say? It's every step of the way. My brain was going, you can't do this, you can't do this, oh my god, this is going to be so scary, you can't do this. And you know what? I could do it. It's easy. It wasn't hard. Yes, I had some problems where I was banging my head against the table going, oh my god, I am stupid, I can't work this out. But the more I started to just think logically, I was able to overcome every single thing here. And it might look like it's trivial. It's not, trust me. I have torn my hair out for 2 weeks, you know, from start to finish on this. But at each point that I've got stuck on something, you know, if I got really stuck where I just can't work it out, I would just drop tools, go away, think about it, and try and think outside the box. Think about, try and apply logic. When you apply the logic to something, think, well, okay, what can I do? What can I do to prove X, Y, or Z? You can then just make those changes, make a few changes to the code, and run your test, and then you go, oh, hang on a minute, yeah, I can see the output enable's not the issue, I can see the heatsink's not the issue, oh, I can see that's not a problem, oh, let's just change this bit of time in here, yeah, that's had no effect, oh, I see, that changes the C path, not the D one, etc, etc. So the point is, I think, you just need determination, is what you need, and you need self-belief. You've got a, you know, that demon or whatever, you know, you've got demons and angels, you've got an angel sat on one shoulder and a demon on the other. That demon on your shoulder, you've just got to bloody ignore it. And trust me, you can do it. You'll be amazed at what you can do. And if you struggle with something to start with, don't be afraid of reaching out, you know, and asking for help from other people. And searching for tutorials and guides and similar projects, and ask for advice, see if anyone can help you, someone more experienced. Yeah, we all stand on the shoulders of giants, is the point. Like, I couldn't have done this project if it wasn't for the inspiration from people like Stephen Leary and Live2 and Mike T and Retro HQ and all the people I mentioned on the credits on the underside of this board. But likewise, I also couldn't have done it if it wasn't for Mattias Heinrichs, yeah? And if you looked at Mattias Heinrichs' life, Mattias Heinrichs would have not been able to do the AGA Multifix if it wasn't for, I don't know, his friends, his accomplices in jobs, you know, teachers, and his own intelligence. It's not like everything's always learned. Everything's not always learned. Sometimes we learn ourselves. We, you know, there's the fixes and things I've done to this that I worked out. No one else worked out. No one went, you need to do this, Chris, and this is the timing for this. Oh, I've worked it out because such and such person taught me. I need to do the timing for such and such and such. No, there are things you work out yourself, but we're not talking about, you know, it's not rocket science stuff, is it? It's me fixing a timing issue with something. The actual implementation to start with, that was all incredible, yeah, but all learned. Mattias learned that. He's learned that through a career, through his life, yeah, from everyone else, from other people, from his teacher, you know, and that's the bottom line, is we all learn and we all teach. But anybody can do anything if you put your mind to it. You just need to learn and teach. Oh, there we go. Back to normal. So you can see everything aligns now, because when I was sampling at 28 megahertz, and our data's at 28 megahertz. Yeah, so anyway, I think those are the majority of things. There were a half a dozen other things that, you know, other problems I had to overcome. We're just talking about small things like trying to understand, you know, what should be fed into a certain pin, what, you know. The 14 megahertz was an example of that. You saw that before. That particular signal, the N-CLK14, was, you know, confusing me. I'm like, is it just 14 megahertz? Is it inverted, or is it just 14? The other interesting behaviour, another problem I had as well, I noticed, and I think it related to the clock domain, when it was on the 14 megahertz clock domain, that code, as I showed you, when you moved that variable cap, we had a square at 0, did you see at the top, you know, around the Commodore thing? When you adjust the trim cap, the pixel was changing. It's like you could see, like, it's almost like you were going between two different displays. You'd move the trim cap and you got one set of pixels, and you moved it the other way, you got another set of pixels. The pixels completely changed, and I'm like, I don't get this. I'm kind of in between a set of pixels. How am I? It's like I'm missing a pixel. That was the final part of that where I went, maybe it needs to be in the 28 megahertz clock domain. So there you go. If you look for clues, you do experimentation, you can uncover the things that give you more information about the problem you're finding. Does that make sense? So there were a few things with that, not just the garbage looking display, but how does adjusting the trim cap affect it? Oh, we can see different pixels. How is that a thing? That shouldn't be a thing. When you adjust that, you shouldn't be seeing different pixels. That, if you like, was the strongest clue there, that was what the issue was, that was sampling on the wrong clock domain. Yeah, I've been testing for about 3.5 hours here, just left this going round and round and round on Super Frog. And it looks pretty good. It's progressive at the moment. We've not got a custom DAC, so in terms of the intensity of the colour, it's lacking a little bit. Sorry, hiccuped there. It looks incredible though, and it's solid. That's the key. Yeah, I was just wondering what these bars were here, but actually looking on the RGB, they are the same. That's correct. So one of the final tests here, testing on this Dell monitor that handles 15 kilohertz stuff, and maybe even higher frequencies. Well, it does, and I'll show you that. I'm just going to go and switch the bypass switch over. Right, I'm switching the bypass switch over, and you'll see it'll go slightly flickerier. Right, that's now bypassed, so that's direct RGB. I can see the flickering here. The monitor is trying to de-interlace the signal. Hang on, the mouse is on the other side of the room. So what I'm going to do is just going to load Agony. Let's just test something that's interlaced, that should flicker as well. And I can switch the scan doubler from bypassing to de-interlace mode, you know, scan doubled mode. So still on bypass at the moment. I'll wait for the game to start. So yeah, that's interlaced, and it's obviously de-interlacing itself, the screen there. And if I switch that over, it's now scan doubled. Yeah, that's working. That's working. I'll switch it back. So the monitor's now de-interlacing, so it'll be a bit flickery. That's the nice thing with this Dell that came from Palmer and Barry. And again, if I switch over to scan doubled, this mode I think has got scan lines on. Yep, I can see the scan lines. So the final thing there was making sure that the scan line mode and the blanking didn't interfere with the bypass. So that was a change I just did. And I also moved from the, I'm trying to think, the rising edge of the 28 megahertz clock for the output enable control to the falling edge. And that seems to have made it a bit easier to dial the 3000 in. It hasn't negatively affected the GBA1000. They did have to just trim the cap just to alter it a tiny little bit, and the resistor, and then it's solid on the GBA1000 and it's solid on the 3000. The point is with this, its current implementation, the code that I've taken from Matse and modified to work this way, it's not a cycle accurate representation of Amber. Now the schematics exist, so at some point either myself or someone else could go away and actually create a cycle accurate, perfect implementation of Amber. But this is solid, and there are a few benefits. If I can't do it now because I haven't got a Super Denise in there. If I was to switch into Super High Res mode, it will display, and obviously it's a sampling thing. You've got I think the timing is reduced for each pixel to 35 nanoseconds in order to achieve it on Super Denise. The net result is the line RAM and the frame RAM has got a limited number of pixels it can hold. Yeah, you've got like 1280 when you go into super high res, and I think the maximum the chip can hold is like 900 and something. But it displays the full screen. But what you're getting is a sampling issue where it's missing a pixel every so often, fitting what is a 1280 pixel scan line into 900 and something. Does that make sense? So you can actually read it, and it's pretty clear if you ask me. But what it is a sampling
you know, it's not sampling at the exact rate, so it's not perfect is the point. But you could then switch the bypass switch over, and I can't demonstrate here because let's say I've got no Super Denise, so I need to buy one, and it'll come out okay is the point. But anyway, the bypass switch is working. I've tested progressive, I've tested interlaced. The bypass switch works. This monitor can handle it. If I do it on the other monitor, it would now say out of you know, unsupported frequency or something. You know, it's 15.6 kilohertz. Someone can't do that. That makes sense. And of course, you'll lose the scan lines because the video is just passing straight through. This is native video straight from Denise with its standard H-Sync and V-Sync going straight to the monitor. Straight to the monitor. As soon as I switch that switch over, it's into scandable mode. So we're at 31 point whatever kilohertz, and we've got scan lines because this particular amber, you know, this marine, has been flashed to have scan lines on all the time in progressive. This is one of the ones that doesn't have jumpers. It's an early, you know, it's the earliest prototype really. So I know this has not been my normal content, but I hope you can appreciate how much time and effort has gone into this. Yes, I had a massive head start thanks to the incredible Mattias. The bottom line is though, the amount of time and the complexity, yeah, it's like this, reconnecting this monitor up. I have been doing this over and over and over because I have limited workspace here and I've got this crusty old monitor, and yeah, it's just been time consuming is the point. And you know, to be clear, I haven't really done this for me. I've done this for me in terms of a learning experience. You know what? It's one of the best things I've pushed myself to do. But it's more about trying to give other people possibilities, not just with a replacement amber, but trying to show you that if I can do this, anyone can, is the bottom line. And again, coming back to the complexity of the code, the initial code from Mattias, had I approached this myself, I could have done it, but it would have taken me a heck of a long time. I'm talking about it could have been a 2 or 3 year project. Because where would I have started if I didn't have a code base? Coming back to the earlier part was just set the screen to a fixed colour, like white, initially. And at that point, if you're starting with no code base, you need to be looking at the syncs, and you need to try and get the syncs the right frequency. So, you know, taking the syncs that are coming in, monitoring them to work out, you know, are you in H-Sync, are you in V-Sync, and doing some stuff to double the frequency. So you'd have to modify those syncs to get the right, you know, scan double, let's just reset that, get the right scan double frequencies there for your syncs, and then just set the screen to a solid colour like white. And from there, you know, there's a number of things, you know, in terms of actually monitoring the sync, the clever stuff he's done there, and producing the, you know, the output sync at the right shape, if you like, with a back porch and a front porch, and you've got that for both H-Sync and V-Sync. That's the difficult bit. That's where you really need a logic analyzer to be able to shape those right and go, yeah, I can see the sync pulses now look as they should be per specs of VGA, and even that has some fluffiness to it, VGA. And what I mean is, you know, I did some research going, you know, what should the sync be for VGA? What about the level? Should it be 5 volts? Should it be 3.3? And it's like, it should be 5 volts, but 3.3 is mostly supported. So I'm like, well, what's that mean? So we've got away with 3.3, so there are some deficiencies here in the design, maybe, that you can argue for really old screen, you know, old setups, old screens, old VGA displays. Maybe the sync might be an issue there. I don't think so. And I think you'll agree, it looks pretty solid. Now on here, I can see, you know, a little bit of waviness, not really waviness, but, well, yeah, if I look really close, I can see a bit of waviness. It's not as good as you may expect, but on the other two displays, it's a heck of a lot better, yeah? And there's another point there. You can see here, we don't see any bands or anything. Granted, we've got a black background, but even on the grey bits at the top, I can't see any banding, yeah? That will appear on many VGA displays, certainly modern ones, LCDs, not CRTs. And it's about sampling again.
because the LCD panel's sampling the signal. You've only got a fixed number of pixels that this screen can display. On a CRT, you don't have that. You've got a scan line that's controlled by, you know, the deflection coils, and the only thing that's a limitation really is, you know, what frequencies the monitor can handle. Yeah, but the point is, as it draws each pixel, there's an analog control mechanism to that scan line, yeah, of how fast it goes to draw the data. So you don't get any sampling going on. It's not sampling it, it's just moving the cathode ray from left to right, flying back, drawing the screen. So you'll always generally get a perfect representation of the image, provided the monitor can handle the frequencies you're throwing at it. With an LCD panel like this, it's got a fixed number of pixels. You're outputting a fixed number of pixels. It's got to try and map that, hasn't it? It's got to try and map, you know, if you're doing, let's say 640 by 200 here, you've got 640 pixels wide. The screen isn't 640. If it was a 640 display, it would look perfect. You wouldn't see any bands. But this is like 1050 type thing. I can't remember the resolution. So you might have, you know, you've got 1,000 and odd pixels there, and it's got to display 640 and display it in a way that it's not just in the middle of the screen just using 640. It tries to stretch it out, so you get a sampling. It has to sample and then go, alright, this pixel's going to be the first one, the second one, the third one, right, we're on to the next pixel. Oh, the first one, the second one, on to the next pixel, first, second, third, and you get a difference. You can't do the maths. Try and divide 1050 or whatever by, you know, 640. You don't get an exact division. Yeah, if you're lucky with some resolutions, you may get a 2-to-1 ratio where you just get 2 pixels for every one, and you get a perfect image, and you don't get any jail bars. Yeah, but as soon as you start trying to, let's say, sample and, you know, approximate things to get things to fit within the display there, you get, every now and again, you see just a subtle change in colour. Yeah, unless the algorithm is really good. Yeah, and I'm talking about like that Dell on the wall back there. Yeah, that has the same sort of resolution as this, but it doesn't show jail bars. They look absolutely incredible, but it does show jail bars on certain modes, so it's not perfect. You have certain screen modes, certain resolutions. Yeah, my TV in the conservatory there, the Philips, the scaler on that's built in, is one of the best I've ever come across. You can throw anything at that and you never see a jail bar. It's incredible how well the sampling and scaling capability of that monitor is. So not all LCD panels are the same, is the point. So hopefully you reached the end of that video. I appreciate it was quite waffly at various points, and yeah, the code bit, if you're not interested in it, you may have wanted to skip over that. So in the next part, we'll do some direct captures of some games and things to show you what it looks like on both the GBA1000 and the A3000, and I'll show you the final revision of the PCB. It's going to be quite short, but we're just going to cover how it actually looks, and I'll just talk about 1 or 2 things that went into the final design of the PCB, talk a little bit about how I opted to route things, because I haven't really covered that. We didn't cover the actual routing side of things. I'm not going to waffle about that too much, just give you an overview of how I laid it out. And talk about the 1 or 2 things that may feed into a future version of this with a PLCC plug. I don't know whether it's worth doing that or not, and potential pitfalls and things based on the final release candidate. So I do hope you found that video interesting. I'd like to thank Mattias Heinrichs again. Thanks to TRU for funding the 2 revisions of prototypes here. That was just brilliant. And thanks to all the people on Ko-fi and Patreon in general, because videos like this just would not be possible without all you guys and gals that support the channel. I am so grateful. This would have never happened if it was not for you. Anyway, I'll catch you in the next video.